In an earlier example, we used a change of variables to change a differential equation into a first-order linear differential equation that was not originally, so that we could solve it. There is a special class of differential equations called homogeneous differential equations, which can be made into separable differential equations, so that we can solve them as well. A differential equation given by the function dy dx equals some function of x and y, where f of x and y can be written in terms of y over x, is called homogeneous. A homogeneous differential equation can be changed into a separable differential equation with the change of variables v equals y over x. As an example, the differential equation dy dx equals 2x squared plus 4xy plus y squared over x squared is homogeneous. We can see this by dividing each term by the denominator x squared. That is, we'll divide 2x squared plus 4xy plus y squared by x squared to get 2x squared over x squared plus 4xy over x squared plus y squared over x squared. In the first term, x squared over x squared is just 1, leaving us with 2. In the next term, 4xy over x squared reduces to 4y over x, and y squared over x squared can be written as y over x squared. So we've written dy dx in terms of y over x, and thus it is homogeneous. Now let's see how we can use a change of variables to solve this differential equation. That is, let's solve the homogeneous differential equation dy dx equals 2x squared plus 4xy plus y squared over x squared, which can be written as 2 plus 4 times y over x plus y over x squared. As noted, we'll need to use the change of variables v equals y over x to solve this. With this change of variables, we can write the right-hand side as 2 plus 4v plus v squared. But we also need to change the left-hand side to be in terms of v as well. To do this, we'll use that y equals x times v from v equals y over x and compute dy dx using the product rule. Doing this, we'll have dy dx equals the derivative of x times v plus x times the derivative of v. But the derivative of x is just 1, leaving us with dy dx equals v plus x times dv dx. We can now write our differential equation in terms of v and x. Using the change to v we just computed, this can be written as v plus x times dv dx equals 2 plus 4v plus v squared. In solving this for dv dx, by subtracting v, then dividing by x, we get that dv dx equals 2 plus 3v plus v squared all over x. This is now a separable differential equation. In fact, we solved the separable differential equation in an earlier video to find that v equals 2kx minus 1 over 1 minus kx for some constant k. So this gives us the function v, but our original differential equation was one of y. So we still need to find the function y that satisfies the original differential equation. To do this, we'll use that y equals x times v, and thus y equals x times 2kx minus 1 over 1 minus kx for that constant k. These homogeneous differential equations give us good examples of differential equations that may not be separable to begin with, but with a change of variables, we can create a separable differential equation that we can solve.